All right, let's meet some heroes and discuss what they did. This is going to be on Newton's three laws. These are scientific laws. You cannot break these laws. It is physically impossible. In fact, that's where the people say, hey, that was physically impossible. You can't do that. That's because they are probably referring to one of Newton's three laws. But before we learn about Newton, we have to learn about this guy, and this is Galileo. Galileo was a very, very intelligent man. He did a lot. So this probably isn't the first time that you are going to encounter his name, and it probably won't be the last. Galileo was very dedicated to the sciences, and so much dedicated that he did get excommunicated from our Catholic Church, which was like the worst thing that you could possibly do back in his time. So let's look at some of his accomplishments. First, we're going to credit him with the discovery of the heliocentric solar system. Helio means sun, centric means center. This is the idea that the sun is the center of our solar system, and all our planets revolve around it. This is what actually got him kicked out of our church, because why would God put the sun as the center when God's main focus is us, humans, and we should be in the center of everything God created, right? Well, it turns out that God decided to put the sun in the center instead, and Galileo was like, hey, the sun's the center of the solar system, not the earth. And the church was like, well, that goes against our teaching, so we're going to kick you out of the church. Eventually, the church did catch up, and we do believe that the sun is the center of our solar system, but it was kind of late for Galileo to be um, accepted back. He's also going to discover that Venus and Mercury have phases, just like your moon has phases. And this is going to lead to the evidence that supports this heliocentric solar system. If your planet is going through phases, and the way that the sun's light reflects off of it says that, hey, the sun, well, it's saying that, hey, the sun is between Venus, Mercury, and then comes Earth. So it kind of puts the planets in order because of that. All the other planets didn't go through phases because they're on the other side of the sun compared to the Earth. He's going to discover Jupiter's moons. Its main four Galilean satellites, Io, Callisto, Europa, and Ganymede. Those are all going to be Jupiter's moons, or the Galilean moons. Some of the coolest bodies in our solar system, actually, if you ever get a chance to look into them. He's also going to look at the acceleration of Earth's gravity as a constant. This is where he stands on the Tower of Pisa and he drops two masses at the same time, and he says the acceleration of Earth's gravity is going to be constant, which is 9.8 meters per second squared, and both of these objects are going to hit the ground at the same time through many tests. This has been proven countless times to be true. Um, and even one of the things they did in space, when they first did space, they recreated his experiments with the absence of that air resistance, which makes it look like one thing would hit before the other. But most importantly, for our purposes, he is going to propose the idea that a net force is the only thing that's needed to stop, start, or change the direction of an object. So once we get that unbalanced force, I can start, I can stop, and I can change the direction of my object, or I can accelerate an object through an unbalanced force. Years later, this man is going to come along, Sir Isaac Newton. Some of his accomplishments are going to be, one, calculus. He is your father of calculus. He kind of derived that math to prove his theories. He worked very closely with Johannes Kepler in calculating the orbits of planets, and helped Kepler come up with his laws of planetary motion. Um, he's going to work a lot with color theory, which is going to be the colors of the rainbow and how different colors combine to make other colors. And he's also going to start quantifying gravity, or in other words, measuring gravity, something that other people have not been able to do. And this is going to lead to his three laws that we will discuss. So he is going to piggyback off of Galileo in publishing his three laws after he did further experiments and derived calculus, which pretty much gave mathematical proof for his laws. So Newton's first law, it states, an object at rest will remain at rest, and an object moving at a constant velocity will continue moving at a constant velocity, unless it's acted upon by an unbalanced force. In other words, if you have a book sitting on a table, that book will continue to sit on the table unless an unbalanced force comes around to move it, such as you pushing it or removing the table from underneath it. This constant velocity is important too, because again, anytime I change velocity is accelerating it. That constant velocity, I need a outside force in order to change my velocity. So in order to slow something down or speed something up or change its direction, I need to have an unbalanced force act on it. If I don't, this object will just continue moving at a constant velocity forever until it does decide to have an unbalanced force acted on it. His first law is also known as the law of inertia. Galileo is actually the one that's going to come up with this idea. However, Newton's going to be the one that can prove it mathematically. Inertia is not a force. Keep that in mind. A lot of people think inertia is a force, but inertia is not a force. It's actually the tendency for an object to resist change in motion. It is actually a physical property. The more mass you have, the harder it is to change your motion. Think about if you're going to, I'll use this example later on too, but if you go to kick a soccer ball, that's pretty easy to do. But if I decide to replace that soccer ball with a bowling ball, it's going to be a lot harder to change that motion because the bowling ball has a physical property of inertia, and so does the soccer ball. The bowling ball has more inertia than the soccer ball, and therefore it's harder to change the direction of a bowling ball than it is a soccer ball by kicking it. Property of inertia. Basically, the more mass you have, the more inertia you're going to have. Again, soccer ball, not that much mass compared to a bowling ball, and therefore the bowling ball will have more inertia. This goes well with cars when you start driving as well. If you have a small compact car, you have less mass and therefore less inertia compared to a giant semi on the semi-truck on the highway, which has a lot more mass and therefore a lot more inertia. It's going to take more force in order to stop a truck than it is to stop your little Honda Civic or whatever you're driving. One reason why trucks need to brake sooner before cars, and why you should give a lot of space between cars and things on the highways especially, and in other roadways. Another example would be like a full bucket would be harder to move than an empty bucket because, you know, the water is going to have inertia to it and it's going to have more mass and therefore require more force to overcome that inertia and get it moving. Newton's second law is a formula that you should have memorized. In fact, this is the biggest formula in all of physics. You should tattoo it on your forehead or wherever you're going to remember it. But this is the formula. Force is going to be equal to mass times acceleration. There's a few practice problems on page 53 you should probably go through, but it is just using a formula like every other formula out there. You just substitute in. As long as you don't know one of the variables, you can calculate it out using your algebra. So here's some examples. First we have an object here. We have the same mass here. This one here, as you can see by the size of my arrow, is going to be given a lot more force. And then this one here, little force. So if I apply a great force to an object, it has a greater acceleration. If I apply the small force to the same object, it has less acceleration. So the more force, the more acceleration, if mass is constant. Here's your soccer ball example. If mass is different and I'm applying the same force, then the object with less mass is going to have a greater acceleration. Again, think about kicking a bowling ball. It's not going to be too pleasant for you as opposed to kicking a soccer ball. Our last one, if you can move my face out of the way here so you can, wherever my face went. Alright, I'm out of the way now. So this is Bob. Bob's pushing a shopping cart, one that's empty and one that is filled with groceries. he's going to use the same amount of force as on both. The one that has more mass is not going to accelerate as much as the one with the empty with less mass, and therefore Newton's second law comes into play. Force equals mass times acceleration. In other words, there's an inverse between mass and acceleration. The more mass you have, the less acceleration you're going to have to a force, or the more force you're going to need to accelerate an object. So basically, to sum it all up, we have the greater the net force, the greater the acceleration, the greater the mass, the smaller the acceleration. So if mass of a rock is doubled, how would that affect the acceleration if the force does not change? Well, if we're going to increase the mass, then we're going to cut the acceleration in half because of that. So if mass is doubled, acceleration has an inverse relationship to it. It's going to be cut in half. We won't be able to move it as much. Newton's third law is a lot of times misrepresented in words, so this is how I want you to say it. But if object A exerts a force on object B will exert a force on object A that is equal in strength and opposite in direction. So a lot of times you mishear this as every action has an equal and opposite reaction. That's pretty much dumbing it down and not really getting the idea of it, though. Basically, you need to have two different objects here. If one object exerts a force on the other object will exert a force on the original object that is equal in strength and opposite in direction. These are your reaction-action forces. So if I fill up a balloon with air, my action is that the balloon is going to rush, or the air in the balloon is going to rush out of it. That is a downward force. Your reaction force is going to be the balloon moving forward or upward due to Newton's third law there. So object A is the balloon, is the air in the balloon forcing out of the balloon, and object B would be the balloon itself moving up. You can think about with skateboards as well. If you're sitting on a skateboard and you push somebody who is also on a skateboard, that person will push you back, equal and opposite, and you will both move away from each other. Rockets are the other big example. Rocket pushes down on the Earth. Earth pushes up on the rocket. That is equal in magnitude but opposite in direction. You can think of Newton's second law coming in place there, where the Earth has a huge mass compared to the rocket. So the Earth's acceleration is going to be less, but the rocket's acceleration will be more, and therefore the rocket shoots up, while the Earth technically does move down, but it's so minute nobody notices, or it doesn't really affect anything in the long run. So action-reaction forces is what we also call that. Newton's third law is going to deal with two forces as opposed to just one unbalanced force on it. They are not going to cancel each other out because these forces are acting on different objects. You have one force from the rocket acting on the Earth, therefore accelerating the Earth, and you have the Earth acting on the rocket, therefore accelerating the rocket. That's why these are not balanced and they do not cancel out, even though they are equal in magnitude and opposite in direction. They are acting on different objects, and therefore you still get that acceleration. So here is your example of this as well. While driving down the road, a firefly strikes the windshield of a bus. It makes a quite obvious mess in front of your face, the driver. This is a clear case of Newton's third law of motion. The firefly hits the bus and the bus hits the firefly. Which of the two forces is greater, the force of the firefly or the force of the bus? Well, it's a trick question. It's Newton's third law. The magnitude of the forces are equal. They're just opposite in direction. Think about the mass of the bus is huge, so you're going to get a small acceleration. While the mass of the firefly is small, and therefore you're going to get a huge acceleration, so much that its body can't take it and it's going to kill it and leave that mess on your windshield. So here's a little activity for you to name that law.